Good day. This is now Module 2, and the first topic is vectors in the plane. We have here the following definitions of vector quantities and scalar quantities. For vector quantities, these are physical quantities that have both magnitude and a direction. You cannot completely define a vector by stating only its magnitude. You must also specify its direction. Example, force, velocity, acceleration, and weight. Scalar quantities only have magnitude but no direction. In other words, scalar quantities are completely defined by a single number with an appropriate unit. Example, time, mass, volume, length, and temperature. We have here now vector in rectangular coordinate system. So we have here vector defined geometrically. The vector represented by the directed line segment AB has initial point A and terminal point B, and its length is denoted by the symbol. It's like an absolute value, AB, with an arrow. Then we say that two vectors are equal if they have the same length and direction. So as you can see in this figure, we can have here a line segment AB, which is also a vector. In this slide, we see here four line segments, which are AB, CD, OP, and EF, have the same length and direction. So we can see that the four arrows in the plane, which are known to be directed line segments, have the same length and direction, and that if represent the same vector, and we write AB equals CD equals OP equals EF. In this slide, we have here vector by components. So we have here in the two-dimensional vector as well as in three-dimensional vector. So for the first one, if V is a two-dimensional vector in the plane equal to the vector with the initial point at the origin and terminal point V1, V2, then the component form of V is V equals V1, V2. So take note of the notation that we use here between a point and a component form of your vector V. So for a point, it is enclosed by parentheses, and for the component form of vector, it is enclosed by angle bracket. Now, if V is a three-dimensional vector equal to the vector with initial point at the origin and terminal point V1, V2, V3, then the component form of V is equal now to V equals V1, V2, V3. So again, as we can see from here, we have here the notation for a terminal point of your given vector V, which is enclosed by parentheses, and the component form of a vector in three-dimensional vector, which is in bracket notation. In this figure, we have here a position vector. So it says here, a position vector is a vector PQ in standard position if it has its initial point at the origin. So we have here the position vector, which is line O. Let's have this as point V. So this is actually also vector V. And the position vector of this vector V is the position vector PQ. So it says here now that the directed line segment PQ and V are parallel and have the same length. So take note from here that your point PQ has this initial point at point P and terminal point at point Q. And point P has the corresponding coordinates x1, y1, z1, and point Q has the coordinates x2, y2, z2. So if you're going to get the component of your vector PQ, that is equal now to x2 minus x1, y2 minus y1, then we have z2 minus z1. That's also equal now to the component of your vector V, which is now v1 minus 0 or v1, v2 minus 0 is v2, then v3 minus 0 is v3. Take note that the coordinates of the origin are 0, 0, 0. In this next slide, we have here the corresponding formula or formulas for the magnitude or length or norm of a vector. So if we have it in two space, where we have here a vector V, it has components v1, v2 in bracket rotation. And its magnitude, represented by this double absolute value sign, is equal to the square root of v sub 1 squared plus v sub 2 squared. So this is when you have your vector v as a position vector with its initial point at the origin. While if we have now a vector represented by the line segment AB, where the initial point is at point A, whose coordinates are x1, y1, and point B, whose coordinates are x2, y2, the component of your vector B now, which is also equal to line segment AB, is equal to x2 minus x1 and y2 minus y1, and in angle bracket notation. So take note that the components of your vector B are obtained by getting the difference of the coordinates of the terminal and the terminal point, rather the terminal and the initial point. And its magnitude now can be obtained similar to distance formula, and that is equal to the square root of x sub 2 minus x sub 1 squared plus y2 minus y1 quantity squared. For our vector in 3 space, we have the vector v, whose initial point at the origin will have the corresponding components v1, v2, and v3 in angle bracket and close in angle bracket. And its magnitude can be obtained by the square root of v sub 1 squared plus v sub 2 squared plus v sub 3 squared. Then if we have a vector whose initial point A and point B are given with their corresponding coordinates for point A, which are x1, y1, z1, and for point B, which are x2, y2, z2, the vector V, represented by the line segment AB, is equal now to, you have x2 minus x1, y2 minus y1, and z2 minus z1 as its component. Again, it is obtained by getting the difference of the coordinates of the 2 points A and B, where we have terminal point coordinates from point B minus the initial point coordinates of point A. And in getting the magnitude of your vector V with this symbol, double absolute value sign, so it is now the square root of quantity x2 minus x1 squared plus quantity y2 minus y1 squared plus quantity z2 minus z1 squared. Then the magnitude or length of the vector v equals pq is the non-negative number. We have the symbol absolute value of v, which is also the double absolute value of v, equals the square root of v1 squared plus v sub 2 squared plus v sub 3 squared is equal to the square root of quantity x2 minus x1 squared plus y2 minus y1 quantity squared plus z2 minus z1 quantity squared. So it means that in this vector v now, whose components are v1, v2, v3, and another vector which is represented by the line segment AB. So we can say now that v1 is equal to x2 minus x1, v2 is equal to y2 minus y1, and v3 is equal to z2 minus z1. So take note of that because in our example later, we will apply this formula. Again, that is v1 equating it to x2 minus x1, v2 equating it to y2 minus y1, and v3 equating it to z2 minus z1. So that involves finding the initial point or the terminal point of a given vector.